and we start our final lecture of the semester. For starters, let me warn you that we are making an experiment. We are testing new equipment, and I thought that I could not miss such an opportunity to test it with a real lecture. You know, there is always a difference between a real lecture and just trying something for 1 minute or two. So I hope it will work. I'm not used to it, so please forgive me if something goes wrong, but I hope it will be better than usual. And because it's the last lecture of the semester, I'm going to prove to you the summarizing theorems. Okay, so I start sharing. And when I start sharing, I will not see you because right now I'm logging only as a host. And could someone confirm that you can hear me? Hello? Can someone confirm that you can hear me?
Yes, we can.
Perfect, thank you so much. Okay, so let's rock and roll. I start sharing. Share. All right. Okay, so I'm going to use this functor, which I defined for you, the finitely supported maps. And remember, I defined it in huge generality. So I defined it as a set of all maps. Oops. From X to K that are finitely supported. But what does it mean? I told you that K is a set which is non-empty and which contains a distinguished element 0. Okay, so these were our assumptions. So finitely supported meant simply that when I take the preimage under F of everything but 0, my distinguished element, then this preimage will be finite. So you see, in particular, when K is a field, when K equals lowercase k is a field, this map f xk stands for finitely supported functions. Because now 0 has a real meaning, right? And another experiment I'm going to make today is I'm going to prove 2 theorems in one go. Because they have basically the same hypothesis and very similar reasoning. We just have to refer to slightly different lemmas. So I am going to write it as one and simply show you alternatives. Of course, in the lecture notes, this is written separately because it belongs even to separate semesters. But this is the summarizing pullback theorem. And maybe I will begin by stating it and stating it in both cases. It's quite lengthy, so please bear with me. But that's the theorem of the semester, if you wish. So let me call it the pullback theorem. Okay, so what is our hypothesis? What it is that we assume? Let the following diagram, I have graphs E, F, and G. E, G, F. And here I have my F0, F1 morphism. Here I have my G0, G1 graph homomorphism. And here I have these inclusions. So this is iota F0, comma iota F1. And likewise here it's iota E0, comma iota E1, the canonical maps. So I want it to be a push-out diagram in the category of graphs, of course, and here is important assumption, and proper graph homomorphisms. So all these maps are indicated here are finite to 1. Such that the following 3 conditions are satisfied. 1, both F0 and G0 are injective. So this is what we call the vertex injectivity condition. Next, our second assumption is that when I have the end of an edge in the push-out diagram equal to the beginning of another edge in the push-out diagram, then both of these edges come from one graph. So formally speaking, I can write that both x, y belong to the image of iota E1, E1, or both of them belong to iota F1 of F1. So this is what we refer to as one color condition. Okay. And here OR is important because it might happen that both X, Y are in both E1 and E2. I mean, the images of E1 and E2. There's no contradiction here. They can be both double colored, but at least they must share one color. That's the idea. Okay, and the third condition, the condition which was not needed for unital semirings, and but which is needed for these semirings which are restricted and for parallel algebras, because now we care about finite to 1. So here's this properness issue. Okay, is that at least one of F1 or G1 is injective. So not both, but one. F1, at least one. F1 or G1 is injective. So this is one-sided injectivity. So basically what we are doing is just the union of graphs except for one but. We allow one of these maps from edges to edges not to be injective but finite to 1. So that's the only generality above just having the union of graphs, okay? But why not? It's worth it. This was the reason why I did everything so pedantically to discover these conditions. Until recently, I had no idea that this would be the hypothesis of my pullback theorem. This was in fact discovered last week. This is sort of the minimal conditions that we need to have things work, all right? So let's rejoice over even slightly bigger generality, slightly less restrictive assumptions. Okay, so this is the hypothesis. Now, what is the claim? Then, and now I have 2 claims. One will be for my not necessarily unital semirings. So I have to dig out other pages to make sure I write it correctly. Okay. So let me do it like this. And on one side, there will be the world of semirings and unital algebras on the other side. So here I can write that RF of a push-out graph is natural isomorphic. That's why I write equal to the fiber product of these semirings. So RFE fiber product over RFG is RFF. So this is on the semi-ring side, and on the path algebra side, of course, for any field K, I have that the path algebra of a push-out graph is the fiber product of path algebras. So KE fibered over KG with KF. And if I were allowed to ask you only one thing to remember from the whole semester, this would be precisely this boxed equality. Okay? So this is your take-home message. Of course, I hope that you remember much more. but if you were just, I don't know, sent to an island and were allowed to take only one formula with you, then I would insist that you take this formula. Okay? But that's not everything. I also want to claim that it comes naturally in the categorical sense. Well, let me divide the screen. Gosh, not minimize, but divide. Why am I doing this? Okay. I told you this is a new device for me. So I'm making some mistakes. Sorry about this. Okay, but that's not the theorem I want. I want yes. So in the semi-ring world, I say that the contravariant functor RF transforms the above push-out diagram to the pullback diagram in the category of semi-rings. Not necessarily in you. Okay, so how does it look like? Well, of course, here we have REF. Here we have RGF, RFF, and here I have the fiber product of these semi-rings. So RFE times RFF fibered over RFG. Okay, well, here are just these pre-image maps, so F inverse and G inverse. And here are the canonical maps. Let me denote them as pi E and pi F for brevity. Okay, so maybe I will do the following. I also want to drag my tools, or maybe I don't have to. Okay, eraser, and I want to erase, well, not everything, but I want to make it shorter. Because now here again I'll have a common part. No, this was a bit too much to the right. Okay, I will manage. So now I have the path algebraic side. Now I can write the contravariant functor. Oh, the contravariant of taking finitely supported maps transforms the above push-out diagram to the pullback diagram in the category of algebras over K. All right, and now we write very similar pullback diagram. So here we have the fiber product of a path algebra, so Ke times Kf over Kg, canonical maps on Ke and on Kf, and then the pullback map. So here I have this F star going to Kg and G star going to Kg. Okay, remember that we defined path algebras precisely as finitely supported maps from the spaces of all paths in a graph into K, all right? So, and also here with F and G, they play the same role on both sides. So this is why I write this explanation jointly. So here, F and G are maps induced maybe let me write it like this. No, I still have one thing to erase. Okay, this will be, we'll have maps from FPG to FPE, and this is my F, and my G goes from FPG to FPF. So here, these are the maps, induced by, and here we write E and the morphism F0, F1, and the morphism G0, G1 going to F, of course, respectively. So that's the meaning. You remember that RFE, but RF is simply of a graph is the set of all finite subsets in the set of all paths, okay? And then this morphism is given by the preimage of the induced map. And for a path algebra, which is defined as the set of all finitely supported functions into a field from the space of paths, well, when we take the map from a space of paths to the space of paths and take its pullback, okay? All right. We have in both cases one more claim about the unitality. So let me write it like this. Finally, if both E0 and F0 are finite, well, then what happens? Again, let me write two cases. Then all semirings and homomorphisms between them are unital, and the diagram, then all semirings and homomorphisms between them, I should say in the above diagram, sorry. All semirings are between them in the above diagram. Oops, what happened? Some spurious lines, completely unintended. Okay, in the above diagrams, the above diagram, the push-out diagram, sorry, pullback diagram, are unital, and the diagram is a pullback diagram in the category of unital semirings. Okay, and on the path algebra side, we say that then all algebras are unital. Oh, sorry, all algebras and homomorphisms between them. I'm too quickly jumping to a conclusion. And all algebras and homomorphisms between them, of course, in the above diagram, but now I mean a different diagram, of course, the diagram of path algebras. Are unital. And the diagram is a pullback diagram in the category of unital algebras. Okay, and that's the whole theorem. I know that there is some repetition, but I think it's still much faster than if I would just write it separately. I don't know how to make it more concise without losing comprehensibility. What you should compare is, of course, that here we have semirings and here we have algebras. And again here, unital algebras and unital semi-rings. So this is in fact the only thing that really changes. Okay, so this is what we have to prove now. Yes? Is there a question? I heard some noise, so. Okay. And the proof will largely consist of bundling up together lemmas that we proved before. Okay. So it's actually a very good theorem to summarize the semester, because now we are going to use, like, I don't know, 8 lemmas or something that we proved before in order to complete the proof of this theorem. So there will be no hard work really right now. All the jigsaw puzzles are already on the table. Now we assemble these jigsaw puzzles into the picture. But the puzzles themselves have been made. We proved these lemmas before, and now we are going to take the benefit. As you can see, these assumptions here are tuned in such a way that the assumptions of all these lemmas are satisfied. Okay. Okay, so let's, if there are no questions, let me now try to write the proof. And again, I'll try to do it in parallel for both cases. Okay. So some things are in common. We have to ensure that our push-out diagram is really a push-out diagram in the category of proper graph homomorphisms without any further assumptions. I mean, this is a little bit tricky, because when I write let blah, blah, blah be a push-out diagram, well, I'm forcing it to be a push-out diagram. So a priori, this might be an additional assumption, like assumption 0, in addition to assumptions 1, 2, 3. But we had this beautiful lemma, there's one injective lemma that allowed us to prove that, well, if our input maps are in the category are proper, so they are finite one, and at least one of these morphisms is injective, then this push out is automatically in the category of proper graph, of graphs and proper graph homomorphisms. Okay, so that's the first statement. This is the lemma which used the assumption, basically we used the assumption 3 combined with assumption 1. Okay, so that's the lemma which used the assumption that everything is finite 1 and at least one side is injective. So for starters, by the one injective lemma, let me write it like this. By the one injective lemma. What was it? Okay. There's this funny noise, but none of us made it. Okay. By the one injective lemma, the assumptions, in fact, 1 and 3, guarantee that the push-out diagram I mean, obviously, it's a push-out diagram in the category of graphs and graph homomorphisms. This goes without saying, okay? But now, because of the assumptions 1 and 3, and by this one injective lemma, we know that this push-out diagram is a push-out diagram in the category of graphs and proper graph homomorphisms. All right, so in other words, we are not assuming that these iota maps are finite to one. This is a consequence, okay? Of course, we could maybe just get rid of this injectivity and then just assume that this is a push-out diagram in a given category. But I don't like assumptions which are close to the claim, because then there is no gain. If I assume something which is very close to what I prove, then I'm not making much of a progress. Maybe this is not the optimal assumption, this one injectivity, but it's an assumption on your input data. It's not an assumption which is hidden, which says, okay, let's take input data such that the results will be such and such, okay? We are giving direct criterion. We just want something which is one injective and everything is finite to one. And then we are home and dry. Okay, so that's the first step, which is common. What next? Then we have a lemma which tells us that the functor of taking all finite paths, the covariant functor, turns push-outs into push-outs, and then we use assumptions 1 and 2, okay? So next. The push-out to push-out lemma. Transforms the initial push-out diagram to the following diagram in the category of sets. And finite to one maps. Okay, so here we have our space of paths in E, our space of paths in F, our space of paths in G. Here we have the induced maps, F and G. Well, and here I have a push out, FPE over FPG with FPF. And vis-a-vis canonical iotas, iota E and iota F. But we know that this is natural isomorphic to FP of a push-out graph. Okay. So then we can view these canonical iota maps combined with this identification as pullbacks of the maps which you have by, sorry, not pullbacks, sorry, push forwards, in fact, of the maps, canonical maps going from E to the push-out graph and from F to the push-out graph. Remember, FP is a covariant functor. So when I go back to my initial push-out diagram, I apply this functor, and I have a functor from FPE to FP of a push-out graph, and I have a map from canonical map from FPF into FP of a push-out graph. But then this lemma, push-out to push-out lemma, proves that this agrees with the canonical maps written here in this diagram. Okay, and again, this is common. This is common for both cases. And here we use, I didn't write which assumptions to use, but remember, we use these assumptions 1 and 2 are assumptions of this push-out to push-out lemma. There's one color condition and vertex injectivity. This is what we need to make sure that this claim is correct, what I wrote here. Okay? And I think this is obvious, but it's really easy. Let me not write it, please. That when you look at these induced maps, it's obvious that if these graph homomorphisms are proper, so both maps are finite to 1, then of course the induced maps are finite to 1. And likewise, if one of these homomorphisms, graph homomorphisms is injective, so both of the maps are injective, then the induced map is automatically injective. That's not so completely obvious, but we all went through this. Remember, this was this argument. Let me make it here as an aside. This was this argument saying, aha, so let's take two paths, E1, En, and say F1, Fn, and they are mapped by my, say, morphism G to the same thing. Yeah, but here we have G of E1, G of En, because this is how graph homomorphism works. And here I have G of F1, the G of Fn. And the equality of paths, so we are trying to prove injectivity. So I assume that this is equal. But this means that G of EI is equal to G of Fi for all I, from 1 to N. Okay, so you see that if G is injective, on the, well, this is actually G1, sorry. So you see that if G1 is injective, then you get that G is injective. Of course, you also need G0 injective, right? Because I'm writing here on the paths of positive length. So independently, you need the injectivity of G0. Okay, but what I'm saying is that injectivity of G1 on the set of edges suffices to have injectivity on the set of all paths. Okay. And the same is with finite to 1. When I take a preimage, the preimage of a path will be bounded by the number of elements in the preimage of a path will be bounded by the number of which you obtain by multiplying the numbers of elements which are in the preimages of respective edges. We also went through this argument. So finite to 1 and injectivity are preserved by these induced maps. Okay. So maybe I'll still write it down here. That preimage of, now how should I write this path? I know A1, AN. This is less than equal than the product over all i's from 1 to n. Now I take preimages under G1 of AI. Take the number. Okay, we have this estimate. So the finite product of finite numbers is a finite number, and in general, this is even smaller because if I take everything in the preimage of a given edge, I might have edges that cannot be concatenated. But surely there are some edges that are concatenated, and this. Anyway, that's the estimate. So finite to 1 remains finite to 1, and injective remains injective. Okay, so that's. I don't want to write it formally because it's really obvious. So I think I even skipped it somehow in the notes or made the reference to a similar reason. Okay, so this way we really see that this is a diagram in the category of sets and finite one maps. That's important because otherwise I cannot apply my functor map F. Okay, and so now we are ready to apply the contravariant functor map F into K. And here things differ. So I again divide my screen to have the left-hand side for semi-rings and the right-hand side for algebras. So here our standing assumption is that K is a two-element set, 0, 1. And here our assumption is that K is lowercase k is a field. So mind you, there is a case in common because you can have Z2, right? Z2 is also a field. So there is some common grounds to this construction. Okay, and here, when K is just two-element set, then I realize that the map F of, say, FPE, okay, is the set. Well, I mean, this still doesn't need to be a set of paths. It can be any set at this level. Let me write X. So this is the set of all finite subsets. And here, will be the vector space of all finitely supported maps. Okay. But remember that this can be naturally identified. We were doing this diagram tracing with RF. Okay, so now take X equal to FPE, and we can naturally identify RFE with 2FFPE. Okay, so I emphasize here the naturality. That's what is our obligation to verify. Of course, I know that I constructed this RFE, where E is a graph, as the set of all finite subsets in the set of all finite paths in E. But I have to make sure that this identification between the set of all finite subsets and all finitely supported maps into the two-element set, that this is natural. And we already did it without caring about finite support. So let me do it one more time, this time caring about finite support. And let me, in fact, use this, write this identification as alpha x, not just equality. I mean, it deserves to be called equality precisely because it's natural, but if I write it as equality from the start, oops, it will not be clear. Working on two screens is not so easy. So I have my whiteboard controls on one screen and my whiteboard on another screen. So I must simultaneously operate the mouse and the pen. Okay, So now this is my alpha x. And how is it defined? Well, we have an alpha x of some map f is defined in such a way that this is a map which maps x to f of x, which is defined as follows. It's 1. Sorry, this is wrong. I'm writing the inverse. Sorry, now I need to have a subset. And of course, this is just the preimage of 1. Which, mind you, this is very important because f is finitely supported. This is a finite set. Okay. Now, well, the inverse is obvious. Well, I was just writing it down, but let me write it anyway. So I take A, which is a finite subset. And now the preimage is defined as a map, which maps x into fa x, defined as a characteristic function of the set A. So this is 1 for x in A and 0 otherwise. So for x not in A. And note that when the set A is finite, of course, fa is a finitely supported function because support is precisely in A. Okay? And now I have this naturality diagram where I have, say, map fyk going to map fxk. So I have some finite to 1 map from x to y. And now I'm taking its pullback. And here I have my identification, alpha y with 2y f and alpha x with 2y f. And here's a preimage map. And this diagram is commutative. Well, we checked it before, nothing changes. The only thing that I had to emphasize right now is that this finite to 1 translates, this finitely supported translates into finite subsets and so on. And I think that we can check the commutativity of this diagram. So I take some function, finite supported function on y. So what is alpha x of f star of I'm so sorry. I used some confusing notation because I used f for elements of this set of finitely supported maps, and I used the same map. Sorry, this should be capital F. Let me make it capital F. So the map, so f is a map from x to y, capital F. Okay, this shouldn't be confused. Okay, so I use f star of now lowercase f. Okay, but this is equal f composed with f preimage of 1. And what if I do it the other way around? I have f preimage of alpha y of f. But alpha y of f is, sorry, this should be f, capital F preimage of alpha y of f, but an end of 1. Sorry, but this is f preimage of lowercase f preimage of 1. So you see that two things agree. Okay. So we have obviously a commutative diagram here. These are the things we don't really have to do on the right-hand side. But I can write that for x being equal to FPE, by definition, I'll find the supported maps from FPE into our field K. This is by definition the path algebra of the graph E. Okay. So here we made a certain identification which is natural, and that's why we can use it freely. But here it's just by definition. So this is why the rest of this page is blank. I don't have to do anything more here to argue. Okay, and now remember we had the lemma. So I'll go to another page. So now, in both cases, we can use the lemma saying that map F mapping into K transforms push-out diagrams in the category of sets and finite to one maps to pullback diagrams in the category of sets. Yeah, we had such a lemma. Well, it's pointless if I just write for you the number, okay? But I'm trying to find it in the lecture notes, nevertheless. There would be a push-out diagram in objective, okay? Yes. No, that's not what I want. This is a lemma which will be used. Yes, and this lemma was proven in an exercise. This was okay. Yeah, but we need this version, not 73 lemma, which is without finite support. I'm using for this version with finite support. 75, so it should be 76. Yes. Yes, let K be a non-empty set with a chosen element 0. Let F be an injective map, and let blah, blah, blah be a push-out diagram in the category of sets and finite one maps. Then this functor transform, contravariant functor transforms push-outs into pullbacks in the category of sets and maps. So the assumptions are satisfied, all right? We have finite to one and one injective. And then we have this lemma, which says, all right, so now these push-out diagrams are transformed in the category of sets and finite one maps, are transformed into pullback diagrams, again in the category of sets, but no arbitrary maps, okay? So that's the lemma which I can use in both cases, whatever the K is. The only thing I assume about K that is non-empty and has a distinguished element 0, which allows me to define this functor of finitely supported maps, okay? Whether it's a field or a set, it doesn't matter. We know that you see, our starting point is the same in both cases. That's this push-out diagram in the space of paths, okay? And it does satisfy our assumptions because, well, we assumed that the push-out of the initial push-out of graphs is one injective and finite to one. So now we know that this diagram is one injective and finite one. So now the lemma applies, and in both cases we get the pullback diagram. Okay, so let me write it down. So we obtain the following pullback diagram. Okay, I can write it as a fiber product. Okay, let me write it like this. Map F of FPE push out with FPF over FPG. But this, by this lemma, we identify with a fiber product because we know that this is a pullback. Oh, sorry, this is comma K. FPE, comma K, fiber products. We find the supported maps from FPF to K, and over finitely supported maps from FPG to K. All right, and here is the diagram. And now for brevity, no, you see, I cannot do it yet. Okay, I'll write it as again, as map F FPE, okay, map F FPF, okay, and here the pullback maps F star, G star, map F FPG to K. And these are the canonical projections. I mean, slot maps, if you know, because this is a fiber product after all. And at the same time, they are just the pullback maps. Okay, and now the whole story is that I can interpret this push-out diagram in the category of sets in two ways. Once I can take this two-element set and talk semi-rings, and another time I can take my field K and talk path algebras. Okay. So hence we obtain now let me divide it, and here there will be this semi-ring R over push out, which you know as a fiber product. Of RFE with RFF over RFG. Here we map to RFE. There we map to RFF. And here we have this pre-image maps, F pre-image and G pre-image going to RFG. Okay, and I can do it so freely now because I just spent some time explaining to you that the pullbacks and the pre-images are identified naturally when we identify the set of all subsets with maps into two-element set, okay? So this is all right, and here we use path algebra. So here this is the path algebra of the push-out graph, EFG, which is a fiber product of KE with KF over KG. And here we map to KE, there we map to KF, and here by the pullback we map to KG, and here again by the pullback, but now a different map, we also map to KG. Okay, and these are my canonical pi e's and pi f's. Okay. But now, so what remains to be done is to prove that these pullbacks are in the right category. Right now, I know. So this is what do we know? We know that this is this diagram is okay. So hence we obtain the commutative diagrams because they're commutative by the sheer fact that we apply functors. But there are pullbacks in the category of sets. So now we have to argue that they are respectively pullbacks in the category of semi-rings and algebras. Okay. But now you see, we know that if we assume, which we do from the start, we know that the input maps F inverse and G inverse, so the maps of taking pre-images, we assume them to be, these are the morphisms of rings. We know that they are semi-ring homomorphisms, okay? Then we already had this discussion that if I have a fiber product in the category of sets, but the defining maps are semi-ring homomorphisms, but what you get is a semi-ring to begin with, and then also all these maps witnessing universality are semi-ring homomorphisms, okay? And the same story will be on the side of top algebras, but maybe it's better to spell it out. Okay, so since F inverse and G inverse are semi-ring homomorphisms, the fiber product RFE, RFG, RFF, which remember, these are all pairs XY in RF E cross RFF, such that F inverse of X is equal to F inverse of Y. So these are compatible pairs by definition. So the fiber product is a sub semi-ring. Of the Cartesian product semi-ring. Okay, so now if you look at these canonical maps, they are slot projections. So of course, slot projections are semi-ring homomorphisms. And if you restrict a semi-ring homomorphism, if you restrict the domain of a semi-ring homomorphism to a sub-semi-ring, of course it will be semi-ring homomorphism, okay? And now when you look at the maps witnessing, okay, maybe moreover, furthermore, all maps we need are semi-ring homomorphisms. Yeah, and what are these maps? Let me try to do this diagram here. RFE, RFG, RFF. Maybe. Yeah, I don't want to go to the previous page, sorry. Now we're using this argument about the enrichment or an enrichment of a category. RFF, okay? So pi E and pi F are now obviously semi-ring homomorphisms. F inverse, G inverse are by assumption semi-ring homomorphisms. And now we need to do one more thing, the universality. If we have some Q mapping here, sorry, if we have some maps over there which are semi-ring homomorphisms, okay, so let's call them JE and JF. If I have such JE and JF which are semi-ring homomorphisms, then of course I know that in the category of sets there exists this unique map H such that the diagram is commutative. But this unique map H is explicitly given in the following way. This map H is just equal to JE, comma JF. So we are mapping we are mapping Q into JE of Q, comma JE of F, and this is a compatible pair because by assumption I have that this outer diagram is commutative. Okay, so this means that H is also a semi-ring homomorphism. I know it's very tedious, but you have to check such things because it happens every now and then that you don't bother to check something tedious and non-exciting, and when it turned out that what you thought was wrong. So I'm sorry for being so pedantic about it, but this is necessary so that you see that I'm not cheating here, okay? All right, and you know, the whole fun was earlier. I'm improving these bunch of lemmas. This is where the difficulty was. Now we are just assembling the jigsaw puzzles into the final picture, which is perfect for the last lecture of the semester. Okay, so now let me do the other side. Since F star and G star are algebra homomorphisms, the fiber product of path algebras KE with KF over KG, which has the same definition, right? Let me not write it down. It's exactly as on the left-hand side. But the fiber product is a subalgebra of a product algebra KE with KF. Right, this is immediate to verify. I mean, really the sheer fact that the multiplication and addition is preserved by a morphism and the neutral element 0 is preserved by a morphism. We know that we deal with semi-rings or subalgebras, okay? Now, furthermore, all maps we need.
Good day.
Any question? Because I hear somebody speaking. Okay. Algebra homomorphisms. Okay, algebra Yep, and in here arguments are really identical. So let me just draw the diagram, but not say the arguments because they are really identical. Yeah, I exaggerated a little bit with these mistakes. Okay, so KG and KF, and here pi E and pi F. All right, so yeah, the arguments are really identical. So I'm not going to spell them out. The only difference is that now we assume that JE and JF are algebra homomorphisms. Okay, and the key point again is that H is just a pair JE comma JF. So we are done. So this proves everything but the unitality. So the theorem is proven except for the last part. You see? Where is this? So this part is proven. We really have these pullback diagrams in the right categories. But now I want to handle this additional situation. Oh, you see, so that's the part which we still have to prove. We have an additional assumption with E0 and F0 finite. And then we have a claim that everything becomes unital. And moreover, these pullback diagrams are pullback diagrams in the category of unital semirings and unital algebras. Okay. Well, this is an easy argument, but still we have to do it. So let's do it. Assume now that both E0 and F0 are finite. Well, oops. Then not only the set of vertices in the push-out graph is finite, but also the zero is finite. And this is because we assume our maps to be finite to 1. Right, it's obvious, but when I have a finite to 1 map and I take the preimage of a finite set under a finite to 1 map, this is obviously a finite to 1. This is obviously a finite set. Okay? Because the finite union of finite sets is finite. Okay, so now everything here is unital. Thus, all semirings and all algebras are unital. Now, how about morphisms? Well, we had an argument that it has already been proven that that these homomorphisms preserve, that these functors preserve unitality, okay? This was part of some lemmas. So let's, I'm just thinking how to write it down succinctly. That's also unit. Furthermore, all involved homomorphisms, unital, basically because the preimage of a finite set under a finite one map is always finite. So now we can do two cases. So in one case, what we are saying is, I take my semi-ring, my unital semi-ring R F, say, well, let me use different names for the graphs A and B, because they are not E, F, G, but this is something generic, okay? I have here the preimage map from RAF into RBF. So F is a map from B to A. Okay. And I'm taking the unit of RFA, which is A0. But of course, this is just equal to B0, which is the unit in RFB. Okay. And likewise here, when I take there is yeah, we proved it, but have I used it? Yes. No, sorry. I didn't, everything is fine. I just didn't emphasize it. So, yeah, I mean, with that S star and D star algebra homomorphism for Pav algebras, this was part of a lemma that we proved for Pav algebras. And this lemma was not so trivial, if you remember. Yes, okay, I just forgot to emphasize it. Yeah, that these we know that these guys are functors. Yes. Yes, these are commutative diagrams in the respective categories. So this is of semi-rings, and here algebras, because these finally supported maps into K are functors. So they map morphisms between, they map maps, which are morphisms between sets, finite one maps. They map them into respectively semi-ring homomorphisms and Pav algebra homomorphisms. But that part is not trivial. Okay, so yeah, I said it, but I didn't emphasize it. So this is commutative diagram here in the category of semi-rings and here in the category of algebras. But we know that they are pullbacks in the category of sets. And then we argued that they are in fact pullbacks in the category of semi-rings and algebras. Okay, sorry, we are good. Okay, so now we have a map from the path algebra Ka to the path algebra Kb. And this is the pullback map, F star. And well, the argument is we did it in our lemma. So said that F star of 1 is equal F star. And here I have the sum of chi v with v running a0, that this is the same as the sum of chi w by the definition of this pullback map F. If you remember, we are just summing over preimages of all these, and if I sum over preimages of all these, I'm taking my w's running the preimage of a0. But of course, this is the same as a0, okay? But this is the same as the sum over w's running the b0 of chi w. And now this is 1 in my path algebra KB. We did it calculation already, but I just repeat it. Okay, and yeah, I think that without any further ado, we can conclude the proof of a theorem. Well, you should still look at the maps, all other maps, all right? But I don't want to draw these diagrams again. So let's look at these diagrams left and right and see that everything is unital. So right now we established that the input maps are unital, okay? So F inverse, G inverse, F pullback, G pullback are unital. And now all objects are unital, basically, by assumption. So now are all remaining maps that we have unital? Well, of course, when RFE and RFF are unital semi-rings, then the fiber product of a unital semi-ring under unital semi-ring homomorphism is a unital subsemi-ring. Yeah, because we have that F inverse of 1 is equal to, sorry, there is a mistake. Why didn't you correct me? This doesn't make sense. This has to be G. Okay, this has to be G. Yep, that makes sense. So when these F inverse, G inverse are unital and the semi-rings are unital, then of course F inverse of 1 equals to G inverse of 1, what we just established or knew earlier on. And therefore 1, 1 is an element here, which is exactly the unit in this semi-ring. So the fiber product is a unital subsemi-ring of a unital semi-ring. And of course, the slot projections are unital. And of course, if we assume that the test maps JE and JF are unital, then of course, putting them together gives us a unital map H, which witnesses the universality. And exactly the same thing on the right-hand side, except that now F inverse and G inverse are replaced by F star and G star by the pullback maps. And here, instead of talking unital algebras, unital semi-rings and unital semi-ring homomorphisms, we are talking about unital algebras and unital algebra homomorphisms. That's exactly the same story. All the maps involved are unital. So this means that indeed, these pullbacks are pullbacks in the category of respectively unital semi-rings and unital algebras. So maybe let me write it down as a conclusion. Hence, our pullback diagrams are pullback diagrams. In the category of unital semi-rings and unital algebras over K respectively. And this ends the proof, which is right on time. We have 4 minutes left. Have you got any questions? Perhaps it's a little bit awkward to do two theorems simultaneously, but I still think that I saved a lot of time. And also, I think it's quite precious to see somehow the unity of mathematics, to see how close these two contravariant functors are. And in fact, you can basically identify them when you take the two-element field. It's just that on at the side of Pav algebras, you have a bit more structure. But set theoretically, then Pav algebra over the two-element field and this semi-ring is the same construction. Yeah, go ahead, yes.
I was wondering if we, because for the path algebras, we choose a field K.
Yes.
And I'm wondering if we, rather than field K, we choose semi-ring, which has two elements, 0 and 1, but 1 plus 1 equals 1. So not the usual Z2, but something different.
Yeah.
If we, in this way, obtain precisely this semi-ring RE. This would be the same construction or something different?
It's possible. One has to verify it. I mean, this is an elementary exercise. I don't know. I haven't done this exercise.
Okay, because it seems like this way.
Yeah.
This one family of.
Sure. I agree. I'm emphasizing precisely this point that perhaps one of the reasons why nobody writes in the literature about these semi-rings is because they are special cases when your field is a two-element field. You can make an appropriate identifications. I don't know if it's the way you said it or some other way, but surely set theoretically they are the same, so there must be some way of identifying them. However, what I find precious in having these two things done simultaneously, one next to another, is that when you talk Pav algebras, you don't even bother to think about this first semi-ring construction, this unital semi-ring construction. But now you realize that there is nothing wrong. You could define some other Pav algebras, so super Pav algebras, where you define them as all maps from finite paths in a graph into a field. There's nothing wrong with it. You'd have the same multiplication. You know, that's sort of the difference between, so we are done with the proof. So that's the difference between having a direct sum, some countable direct sum of vector spaces, and the product. So here we have finite sequences and arbitrary sequences. That's this map F. FPE sitting inside all maps FPEK. But I've never seen anybody considering such Pav algebras. There's another issue which you might wonder, how about not restricting ourselves to finite paths? You can concatenate also infinite paths and you can assign some things to that. Yeah, that's another story. But this one is immediate. We do have such an ambient algebra, which is always unital. And the Pav algebra we consider is a subalgebra of this unital algebra. I don't want to say that these are like multipliers, but that's what first comes to your mind, you know, functions vanishing in infinity and bounded functions. And I wouldn't dare to think about path algebras, about such possibility of extending path algebras without the semi-ring construction. Because the semi-ring construction, it's far more natural just to take all subsets. When you just handle sets, you don't worry. When you have sums of a sets, you begin to worry. Is it convergent? Does it make sense? Yeah, here it does, because you're sort of adding things at a different slot. So the infinite sum is natural convergent. Okay. I can have support function. You know, say chi I of j is equal delta ij, and I can have infinite sum of chi i's. And then this will be 1 in my algebra. And it makes perfect sense. In my algebra, I know from end to end. Okay. Yeah, but you know, if you don't like the semi-rings, you can forget them. They are not essential. I treated them as a kind of warm-up test ground, you know. But what is absolutely essential, and this is your take-home message, is the pullback theorem for path algebras. And by digging so deeply into graphs, we managed to distill the optimal assumptions, in my opinion, for the pullback theorem. And these assumptions are that these 1 to 3 assumptions, okay? So we are in the category of course, proper graph homomorphisms, otherwise forget it, the functor doesn't apply. But then we need these extra assumptions, right? The one color condition, vertex injectivity, and this one-sided injectivity. Under these assumptions, which are still more relaxed than an assumption of having the union graph, we have a pullback theorem. So from the push out of graphs, we obtain the pullback of path algebras. And this is the most essential take-home message from the whole lecture. And I think this is a good time to stop. I'm still, I believe if time permitting, I'm going to review the course during the recitation class. But now let's make a break and resume at 11:30. I stop recording. Thanks. First, I have to stop share. And now, stop recording.